Good evening, everyone. Welcome to the sixth class of Biostatistics and R. I am seeing that we have a very less population today, but that's fine. Let us just get started. Okay, today we will be covering. So, last we had covered how exactly descriptive statistics work and what the central tendencies, mean, median, mode, and how to use them are. Today we are going to go in a different direction and learn about how exactly do you test different hypotheses you on your data set using statistics. So whenever you have a set of data, the first thing you have to do is start with a hypothesis or a question that you want to ask. You obviously have something you want to research, and that is why you are looking at the data set. So a research hypothesis could be anything. So it could be an idea that can be tested with observations and experiments. So you have to ask a question which is a correct question with respect to the data set that you are working with, and so that you can actually experiment on that and figure out if your hypothesis is correct. Examples could be lack of sleep reduces ability to memorize things, or say extrasensory perception, or ability to know something that shouldn't be obvious exists or not. So these kind of questions can also be research hypothesis, but then you will have to set your experiment and gather data correctly based on these. So when uh, so when you are dealing with a statistical hypothesis, like you have your data already, you have to like how exactly do you design your experiment. So when you do a statistical hypothesis, I should put it somewhere right here. It has two parts. First is a null hypothesis. So you have asked a question, you based a hypothesis on that, and then you asked a question based on that. So and how you do that is that you make two hypotheses. One is called the null hypothesis that rejects your question. So say for example, you were tossing a coin, and obviously in a fair ideal situation the probability of heads should be 50%. So now your idea is that but your question is the coin fair or not. You form a null hypothesis then that the probability of heads is 50%, and an alternate hypothesis that the probability of heads is not 50%. And the entire idea behind your experiments would be to reject the null hypothesis. So you are actually trying to prove the alternate hypothesis, but you don't go about doing that by just proving the alternate hypothesis. You actually reject the null hypothesis, and that proves the alternate hypothesis. So this is because people have figured out way back when that if you try to prove something, it is very easy to prove it, but disproving something is where the difficulty comes in. So when we have a alternate hypothesis, if we start trying to prove it, we will be able to prove it very easily, but rejecting it is where the trick comes. Rejecting the null hypothesis is how you prove the alternate hypothesis. You do not right off the bat say that this is my hypothesis, I am going to prove it right. That doesn't is not how it works. You have a null hypothesis which is completely opposite to your alternate hypothesis, and then you reject the null hypothesis. So the entire point is that it is a null hypothesis versus an alternate hypothesis. And our alternate hypothesis, what we want to prove here is that, okay, what we want to prove here is that the coin toss is not fair. So our null hypothesis would be that the coin toss is fair, and then we want to prove the validity of the null hypothesis, if it is true or not. For our example, say you were tossing a coin. How would you know that the coin is fair or not? So you go about it in the other direction. You to try to prove that the coin is fair, and when that doesn't work out, the only other solution is that the coin is not fair. So our null hypothesis is the coin is fair, and the alternate hypothesis would be that the coin is not fair. So examples of how to exactly design experiments such as this, uh, one could be cats show no preference for food based on shape. So if you have cat food which is shaped like fishes as opposed to any generic other shape, do cats actually prefer the one that looks like fishes, or it doesn't matter at all? So if you want to prove that, the null hypothesis would be the cat show no preference for food based on shape. Similarly, if you want to see if you have a garden and you have lamps to light up the garden, and want to test does the plant growth is the plant growth affected by light color, then your null hypothesis would be that the plant growth is not affected by by light color, and you want to reject this in order to prove your hypothesis that actually plant growth is affected by light color. So idea is, when you want to ask a question, you want to design a hypothesis, you want to prove something, you make two hypotheses. One is a null hypothesis, one is the alternate hypothesis. If the null is not possible, then the only other way is the alternate is the truth. So your entire idea is to prove or disprove the null hypothesis, and that will in turn prove or disprove your alternate hypothesis. Everyone with me so far? Okay. So, but while doing this, statistically there could be a number of problems. So the major problems when analyzing data sets and trying to prove or disprove the null hypothesis are known as the type 1 error and the type 2 error. Type 1 error is called the false positives, where false positives, we all know, we have heard of it, when we were going for RT-PCR tests for COVID, there was a big scare that you could be false positive, that you actually do not have COVID, but you have been tested for COVID and it came back as positive in the RT-PCR test. So this is known as a false positive, where you should have you should not have rejected the null hypothesis, but you did not. So you should have rejected the null hypothesis, that is your alternate hypothesis was false, but you went ahead and accepted it, and you proved that your alternate hypothesis is correct. So this is known as the type 1 error, in which the null hypothesis is rejected, but your alternate is false. So null hypothesis should have been retained in this case. So that is known as the type 1 error. The type 1 error is shown by probability alpha. The other type of error is type 2 error. So these are false negatives, in which your alternate was true, but you ended up accepting the null hypothesis and proving that your alternate is false. This is shown by the probability beta. So type 1 error alpha, type 2 error beta. Type 1 error, when your null hypothesis should have been accepted and your alternate was false, but you ended up actually rejecting the null hypothesis and proving that your alternate assumption was correct, and that caused a type 1 error. For example, you are tossing your coin and trying to figure out if the coin toss was fair or not, and it was not, it was actually fair, but you rejected that null hypothesis because you got 3 heads in a row, and they were like, yes, this coin is absolutely not fair, I am not going to play with it. That is the situation where the type 1 error occurs. Type 2 error is when you toss the coin, say 4 times, and you get head, tails, head, tails, head, tails. And you are like, okay, so it seems that the coin is fair because I'm getting a 50% probability of heads and tails. So you go ahead and retain the null hypothesis and say that the coin toss is fair. But actually the coin was not fair, and you have done a type 2 error in which you retain the null hypothesis and caused the but instead of accepting the alternate one. These are type 1 and type 2 errors when it comes to rejecting or retaining null hypothesis. So there are levels to all of these. Type 1 and type 2 errors have levels, and the accepted levels could be for alpha 0.5, 0.05, 0.01, 0.001. We will see what it means. So here is our question. If you have 62 heads out of 100 tosses, is the coin fair or not? So this is our question that we want to prove. So can anyone tell me what the null hypothesis in this case would be? There are 62 heads out of 100 tosses. What should be the null hypothesis?
The coin is fair.
Yes, the null hypothesis would be the coin is fair. So you want to reject the null and figure out if you can reject the null, then you will actually say that the coin is not fair. If you accept the null, then you will say that the coin is fair and nothing is a problem. So this kind of so explaining it would be easiest if I show you what do you call it, distribution of frequency. So this is a graph known as a normal distribution. This is what happens most of the time in nature. So how it happens is that in the x-axis you plot a set of possible results. In the y-axis you plot the probability of observation. Essentially, you can imagine it being the marks that we get in a class test on the x-axis, and the number of people who have gotten those marks. So if you imagine it like that, obviously most of the people would be right here in the middle. The middle would be have a higher frequency, so it is like a hill here. And then you have on both ends very unlikely observations where people have gotten a very good result, say 95s or 100s. And similarly, on the other end, you also have very unlikely results like people getting very low marks. So this is how you plot a distribution, uh, a normal distribution can occur under these cases. So there are two things here that I want to draw your attention to. The middle of it, so this is what the original distribution should look like. So you know, yeah, the if the test was pretty average, most of us would get somewhere in the middle. Some of us would get very good marks, some of us would get low marks. But if the test was truly very hard, then you can imagine that the entire middle portion would actually shift to the left. Everyone got low marks. If the test was very easy, then the entire distribution will shift to the right. Test was too easy, most of us got very good marks. But overall, the shape would remain like this. Is that okay? Okay, so now how do you know that the test was not either not too hard or not too easy? So it also so this is how you test it. You look at the tails of the entire distribution. Tails are these portions that are dying out. We were talking about these last day also. These portions where there are extreme values, and you decide a statistically significant threshold. Say the extreme 95%, either either way, either in the higher direction or in the lower direction. So this is called a statistical significance threshold. Most of the tests either have a 95% statistical significance threshold or even higher, and this is where the graph should have started dying down. But your observation, like you saw that most of your data lies after this. So that gives you the idea that if there is a lot of data after this, obviously the test was too easy because it is not saturated in the middle, but it is towards this side. So this 95% statistical significant threshold is where our alpha values lie. So this is our type 1 error bar. If this is crossed, then our null hypothesis would get rejected. And how do we know that? We use an identifier called p-value. So if, say, the same example, if I take it here, say mean score of the class, and obviously most of it lies in the middle. Some of them lie in the higher region, some of them lie in the lower region. So this is a sampling distribution. So sampling distribution, as we had seen last class also, you take a small amount from the entire population and you plot it, and you try to estimate the parameter of the entire population using the samples that you have taken. So there is a concept called critical regions. These critical regions are these tails of the distribution, and here is where the null hypothesis would either be accepted or rejected. So critical region is at the tails of the distribution and corresponds to the value of alpha. So what that means is that if most of my distribution lies in these critical regions, then obviously something is wrong and the null hypothesis must be rejected. And if most of my values remain in the middle, then the null hypothesis was correct all along, and null hypothesis should be accepted. So if it is in the middle, the test was pretty nice. If it was on the higher end, then our test actually was very easy. If it is on the lower end, the test was very difficult, and most of our students actually scored pretty low. So when you are constructing a hypothesis, these are what you take into account. First, you define a alpha level. So what is the level? So alpha levels, so it indicates the tails of the distribution, and if your values majorly lie in the tails of the distribution, then you say obviously then my null is wrong. So first you do is take a alpha level, then you decide what are you trying to test. So test statistic, then depending on the statistics, say here we are taking the example of marks of all the students, you make a sampling distribution, and then you look at the critical regions, and after all of this you decide if you want to reject or accept the null hypothesis. So as I said, you do this via a parameter known as the p-value. The p-value determines if your particular experiment or study has values in those critical regions or not. So first you have to decide on the value of alpha. So I can show it to you easier here. So alpha is chosen to set the standard for rejecting null hypothesis. So how much should the entire distribution be skewed for you to either accept or reject the null hypothesis? And p-value indicates the value or the how much your experiment is skewed. So you first decide, yes, if my coin if I toss it 100 times and it comes as 80 heads, then I will say ki my coin is not fair. And then you actually toss it 100 times and see if you have 80 heads or not, and that gives you the p-value. So this you decide before your experiment. This is what your experiment gives you. So this is how it occurs. Normally p-value, so normally p-value should be less than 5% for a test to be significant. If it is greater than 5%, then you say that the test wasn't significant, you couldn't reject the null hypothesis. So you toss the coin, and instead of getting 80 heads, you figured out it only got 52 heads. So it is more or less the same as getting tails. So the test was not significant. Now p-values come in a lot of like lot of number, what do you call it, levels. So if your p-value is less than 5%, which means that your distribution is actually skewed more than, like more than 95% to either end, then you have a 1-star significant. So you can reject the null hypothesis, but it is barely significant is what people say, but it is still significant. If it is less than 1%, then it is a 2-star significance, and if it is less than 0.1%, then it is very very significant. So you definitely know ki something is wrong with the coin. So even at 1-star, depending on how you have constructed your experiment, even 1-star could be a pretty significant result, but most of the time people look for these 3-star results that actually there is some significant change in the results, and you can definitely reject the null hypothesis. So this is something that we can do on R. So you can boot up your R Studio. So this is what we are trying to do. So a coin toss is, as you would say, imagine a binomial experiment, right? It can either be a head or a tail. So you can do that in R using the binom test function. So here x is the number of times you get a positive result, so x is the number of heads, n is the total number of tosses, and p is not actually the p-value. P is the expected probability of heads. So if I uh, tossed a coin 100 times and I got 50 heads, this is the situation, and obviously I imagine that the coin is fair, so my probability should be 50%. So if I run this, I get a result like so. So this is the exact binomial test. Data is 50 heads and 100 tosses. So number of successes are 50, number of trials are 100, and the p-value is 1. So if a p-value, as I said, if so this p-value is not this is the probability, the p-value is coming as 1. So our idea was, if the p-value is less than 0.5, then we would be able to say significantly that the coin is not fair. Here we are getting a p-value of 1, which is pretty high. So the coin, so it is actually a 100% p-value, there is no problem at all, the coin is fair. So if I actually start increasing now, if it was 52, you see the p-value changed. You now have a p-value of 0.76, that your distribution, that your data point is, so data point, so this is, if I plot, imagine this to be the number of heads and tails, most of them should have been here, but now your data point is somewhere over here. So you are getting 50, instead of a 50% heads, you're getting 52. So your data point is shifting. but the p-value tells you that it is still in not in the extreme skewed region, so it is still not significantly, like you can't significantly say that the coin toss is unfair. So can anyone try and tell me that like if you can open up R Studio, and where does the p value actually dip down below 0.05, so 5% of 5% of the entire distribution. So you can keep on changing this x value till you get a p value of less than 0.05%. Can anyone try and tell me?
Sir, the p-value has to be less than 0.05.
Yes, so for significant results, you have it has to be less than 0.05.
Sir, for some reason, my p-value is constantly showing in E format, like 7.85 E minus
So your p value
0.05.
is very 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 low in that case. So obviously you are getting
Okay,
significant results. So if you do like say 95 heads out of 100, obviously the p value will go ridiculously low. Yes, obviously your coin is unfair.
got it, sir.
Sir, at x equals to 61, the p-value is 0.0352.
Okay, so our initial experiment was if there are 62 heads, can you say that the coin toss is unfair? You can actually say that it is unfair because your significant p-value is less than 0.05. So this is how you test, like you make a null hypothesis, you test the null hypothesis using experiment, and you then figure out the p-value, and the p-value tells you if your results are significant or not. So obviously if there are 62 times you have heads out of 100, your coin is absolutely not fair. Is that okay for everyone?
Sir, I have a confusion. That is, we assumed the null hypothesis as coin is unfair or the coin is fair.
Coin is fair. You wanted to prove
Okay.
that the coin is unfair. So your null hypothesis will be the opposite one, that the coin is fair. So this is pretty much the entire p-values and how to actually prove them is the entire idea behind doing statistics and tests for us at least. So if anyone has any questions, please pipe up and let me know.
Sir,
Yes.
sir, I have a question that is, while we are assuming the null hypothesis to a particular question,
Mm-hmm.
so should it be like assuming the false, like say assuming that how many heads or tails would be coming in a toss.
Mm-hmm.
So for that, the null hypothesis should be like that the coin is fair. Means we should assume that it's a like the assumption should be of a true statement or a false statement.
The assumption, the null hypothesis should be what the general case is. So say for example you are taking you were researching a drug to figure out if you can treat cancer or not. So you had two drugs, drug A, drug B, and then you had water, which does nothing obviously. So when you start putting testing these drugs, you check, you want to prove that drug A actually treats cancer better than water, or drug A is better than drug B. So your null hypothesis should be So what is what you want to prove? Drug A is better than drug B. Then your null hypothesis should be drug A is as effective or less effective than drug B. Then you try to reject the null hypothesis, which will prove your alternate hypothesis that the drug A is actually better than drug B. So how this happens is that you figure out what you want to prove and you make a null hypothesis which is completely opposite to your case. So if the null hypothesis is not true, the only other thing that could be true is your alternate hypothesis. This is the idea behind it. So here we want to prove that the coin is not fair. So if I assume that my null hypothesis is the coin is fair and I reject it, I am able to reject it, then the only thing remaining is that my coin is unfair.
Okay, sir.
Okay. Anyone else that wants to ask anything from this? So we will always, so this is a very easy test we did with binomial data. Later on, when in the next class, we will be looking at other tests to actually figure out the difference between, see, two different data sets. Say you wanted to figure out that the average height of BSB department is taller than CSC department. In that cases, you actually have to choose different set of tests. In that case, you will use something called a t-test, and there also the value that you look for is the p-value. This is what you will look for, and if you get a value which is less than your selected alpha, which is either 5% or 1% or 0.1%, you can say yes, significantly I can say that BSB people are taller than CSC people, or the other way around. So this is what we want to do here. So that was about alpha and the p values and how to deal with them. Next, we are going to deal with the type 2 error. So type 1 error was when you are accepting the null hypothesis, no, when you are rejecting the null hypothesis with, whereas you should have accepted it. So it is a false positive. So you are saying yes, my test was correct, yes, there is a change that is occurring, yes, the drug A was better than drug B, but that was not the case, and you figured that out using the p values. If your test was significant and your p value is less than 0.05, then you are not committing a type 1 error. It is not a false positive, it is actually significantly proven that the coin toss was unfair if there are 62 heads out of 100. The other way is the type 2 error, where you actually wrongly accept the null hypothesis when the alternate hypothesis was correct. So you wrongly said, okay, so my coin was fair, but that was not actually true. So you accepted the null hypothesis when the alternate was the truth. So this is called beta or type 2 error. So if beta is the probability of making a type 2 error, then 1 minus beta is known as the power of a test, where you are correctly rejecting the null hypothesis. So here you are wrongly accepting the null hypothesis when you should have rejected it. So 1 minus beta should be the probability that correctly rejecting the null hypothesis when it is wrong. So you are not making any type 2 errors. Minimizing beta means maximizing power, because power is 1 minus beta. So if you minimize beta, then you maximize the power of your test. So say we have another example here. This is an example of another time you are doing the coin tosses, and you not coin tosses. Say this is the same as the previous example where we are taking the mean of marks of everyone in the test. So it was a very easy test. So everyone actually scored close to 70%. So your entire distribution is shifted towards the right. So your entire distribution, most of the mean is around 70%, and it is completely in the middle. and whereas very less amount of people actually scored, and you can see very small, one or two people actually scored less. And so your upper critical region, so the original normal distribution should have been, the middle should have been here, whereas now it is shifted here. But if you now look for, so if you look at this tail you look at, you can obviously say yes, everyone scored very high, the test was very easy. But if you look at this side, it looks more or less similar to what it should have looked if the middle was right here. So in this case, for data below 60, the null hypothesis would be accepted that the test was fair, the test was pretty okay, because the number of people who would have scored low are also scoring low here if you just look at this end of it. So in this case, you are actually rejecting the accepting the null hypothesis, even though obviously looking at the other end you could have figured out, no, the test was very easy, the entire mean has shifted, everyone is scoring hugely high marks. So for these data, even though the alternate hypothesis is correct, null is wrongly accepted. So this, the idea here is that this is the distribution of the entire population. So population, if you looked at, say this was a huge exam, say this was the gate exam, and if you looked at the like thousands and lakhs of papers, you could have figured out, yes, after plotting all of them, most of them are in the higher section, the exam was very easy. But as we have been saying, that this is most of the time not possible. You cannot go ahead and look at the entire population. You pick and choose samples, and if you had unluckily or in a biased way chosen samples which showed the lower critical region only, that everyone was actually scoring very low marks, and only looking at that you decided ki yes, okay, it's fine, most of them are choosing low, most of them are getting low marks, the test was actually fairly okay, because you probably get a distribution which looks very normal looking, with the mean here, because you have not looked at that many samples. So can anyone tell me how exactly can I figure out, like how can I increase the power of this test? So if I wanted to actually be able to figure out if I am wrongly accepting the null hypothesis, how exactly can I do that? Like say, same example, gate exam, most of the people have scored highly, but I am choosing a very small sample, and that is causing me to get a moti normal looking distribution, and I'm looking at the lower end where it is pretty normal looking. So how can I increase the power of the entire test? How can I figure out that I'm wrongly accepting the null hypothesis? Any guesses? You can go ahead and try anything you want. Like, give me a guess. What do you think is the situation? Like, how can I increase the power of the test? How can I figure out that the null hypothesis that I am accepting by looking at this region only is false? Like, what should I do? I can give you another example. Say the same coin toss example was the one that we are dealing with. So in that, we had seen that if you have 62 coin tosses which are heads, then out of 100, then you can actually say yes, the coin is unfair. But if I only tossed it, say 5 times, and see, similar 60% of it would be, say, 3 heads and 2 tails, you wouldn't have been able to figure out that the null hypothesis is wrong, right? Because there is not many, like, you actually, it looks very fair, even though it is still a 60% distribution towards the heads. It is obvious that out of 5, 3 could be heads. the like why 3 should be heads, like it couldn't go any other way. So what exactly did we do to increase the power of the test? How did we figure out that the coin is actually unfair? Any guesses, anyone?
Sir, could you repeat the question?
Say we go back to our coin toss example. We know if they out of 100 coin tosses, if there are 62 heads, then we know that obviously our coin is unfair. Say you had a similar situation where you're just tossing the coin 5 times. In that, a 60-62% probability of heads would actually be around 3 heads out and 2 tails out of the total 5 tosses. So how in that case will I, like, what am I doing wrong? Like, because in that 5 tosses I am actually getting a p value, the same, you will get the same p value, but you cannot actually reject the null hypothesis because it looks very okay. So if I show you on the R studio, if I did, instead of 62 and 100, if I did a 3 and a 5, see, the p value is not significant, even though it is still a 0.6% probability of success, which you remember if I did this, the probability of success was still 0.62, but we had significantly proven that the coin was unfair. But in the same case, if it was 3 and total number of trials were 5, the probability of success is still zero point 0.6, but we are not able to significantly reject the null hypothesis because the p value is not less than 0.5, it is 1. So yeah, actually 0.05. So how, what is, like, how, so this is how, what you call a underpowered test. So how will I be able to fix this? What am I doing in the first example which I am not able to do here? Okay, I will give it away. So the best, so you, uh, let us get something clear. You understand that in this case we are committing a type 2 error. The coin was actually unfair, but we are accepting the null hypothesis and saying it was fair. Anyone has any doubts about it? Yes, no, something. So if I write, where will you write that down? Null hypothesis, coin is fair. Alternate hypothesis, coin is not fair. So in this test we saw that p value was not significant, so we are not able to reject the null hypothesis, so we are saying that the coin is fair, even though we know it is not fair because the probability of success is zero point 0.6, but we are not able to prove otherwise. So how is this different from when we were doing a larger number of tosses? Same probability of success, but now it is significantly, we are significantly able to prove that the coin is unfair. So this is how you avoid This is how you avoid the type 2 error. You increase the number of trials in any kind of biological, like any kind of experiment, especially biological ones. You always talk about increasing the number of n's. You increase the number of experiments in which you are getting a positive result. Till you get a lot of n's, you cannot positively eliminate the null hypothesis. You cannot say you're not doing a type 2 error. In that case, we say that the study is underpowered. You have to increase the number of trials. You have to test it on more people. You have to do it multiple times. You have to do it on multiple cells. You have to do it on multiple ends, like embryos, anything. You increase the number of experiments, and that is what is known as a powerful study. You increase the power of the study by increasing the number of n's, or you design a better experiment where you have a better, like you have a less chance of committing a type 2 error. So in this case, you understand that the type 2 error was occurring because our number of trials was very low. If I increase the number of trials, then our type 2 error goes away. So this is how you design a powerful experiment. You avoid a type 2 error by testing it on more people. So best example of it would be when we are looking at clinical trials for drugs. We have phase 1, phase 2, phase 3 trials that we are talking about the last day. You don't test your drug out on 10 people and say it is fine for the entire population. You don't do that. You take a first phase 1 trial, you are dealing with tens of people, 10 to 50, then there is no problem. Then you go to a phase 2 trial when you are looking at hundreds of people. Then you go to a phase 3 trial when you are looking at thousands of people. You are increasing the number of n's so that the power of your test actually increases, and you can positively say this drug is working and it does not have any side effects. That is how exactly you design a powerful experiment. That is what we call as reducing the type 2 error. Is that fine with everyone?
Yes, sir.
Okay. Honor Shabai, everyone is okay with this.
Yes.
Okay. So how can we increase the power of our study? So this is what is occurring. So p value is greater than alpha. So this is what we saw when we were doing a lower amount of trials, uh, lower amount of trials. Here our p value was less than 0.05, so alpha here is 0.05. We are doing a lower amount of trials, our p value is greater than 0.05. We can't significantly say that our test is, like we can't significantly reject the null hypothesis. So this is the condition here, that our p value is greater than alpha. So it could be that the null hypothesis is actually correct and you cannot reject it, or that the power of the test is low. So you have to somehow tune it, and uh, that you do by either increasing the n's or the effect size. So you design your experiment better. Or the other case could be that if your n's are sufficiently big enough and the hypothesis is actually true, and there is no significant difference between drug A and drug B, or say your coin is actually fair. But you have to always make sure that you have a, like, do not have a underpowered study where you cannot actually conclude because your either the n's are very low or your effect size or design is not very nice. So how do you do a power analysis? So before doing any kind of experiment, you have to figure it out, like what should be your alpha under which you will say that yes, I can significantly reject the null hypothesis. What should be the beta, which also tells you that the how powerful the study needs to be, which in turn will determine the number of times you have to do it. So the so that actually gives you the idea if the study is time wise and resource wise very feasible. Why do I say that? Say your particular experiment, like say the coin toss experiment only, when you are tossing it 100 times and you are getting a 62 times you are getting head, you could say yes, your coin is actually unfair. But how many times would you do it before you could actually say yes, my study is powerful enough to reject the null hypothesis? It could be in another scenario you have to do it 10,000 times before you could positively say yes, my test is now powerful enough to tell you that the null hypothesis is incorrect. So that gives you an idea if the study should be undertaken or not. If you have to do it a large number of times, which is very time consuming and resource consuming, you might not be able to actually do the entire experiment. So is this kind of a thing should also come into your mind when you're designing an experiment. So this is a graph. So this is the sample size and this is a coin toss experiment only. So this is the possibility of rejecting the null on the y-axis, the number of times you're tossing the coin. As you can see, when you go to close to 100 n's is when you can actually always, like with a probability of 100%, say that the test is powerful enough and you can reject the null. But if you stopped at say around 50, you only had a 70% chance of rejecting the null with your test. If you say did 20 times, 20 tosses only, it is also very low. You couldn't reject the null hypothesis significantly because your test is not powerful enough. So increase the number of n's and that gives you a powerful test to deal with, and you can actually not commit a type 2 error. That is, you can positively reject the null hypothesis and prove what your actual result is. Now the question is, how many times would you do it? Like, how would you know that your how would you know that this is the correct number of times I have to do it? So say your coin was very slightly unfair. So very slightly unfair would mean, going back to R, say you tossed 5,000 times, and out of that, the number of, if it was a very fair coin, it should have been a 2,500 heads and 2,500 tails. But you got 2,505 number of heads. So if your coin toss is slightly unfair, how many times should you have to do it to actually prove it? So say your drug A versus drug B, which both of them treat cancer, drug A was so slightly better than drug B that you, doing 100 trials, you couldn't figure out the difference between them. So what is the number of times would you do it? Would you keep on doing it infinitely till you actually find a difference? You keep on increasing the power till you actually are positive that you can actually differentiate between both of them. So what is the point that you stop, that you say that this is the correct number of n's that I should have done and for my particular experiment, and now I can actually stop and say that if the p-value is still greater than alpha, we can accept the null hypothesis, or if it is less than alpha, then I can reject the null hypothesis. Are we on the same page? বোঝা গেল কি না যেটা বলছি? So what I want to say is that increasing the number of trials increases the power of the test. But how do you know that what should be the ideal number of n? You understand what I am talking about, everyone?
Yes, sir.
Okay. So how do you do that? There is actually what do you call it? A statistical parameter known as Cohen's h. So this small h. So I will type it out for you. Okay, so okay, so as I say, we are talking about Cohen's h, this small h parameter, which actually looks at the difference between two distributions. So here there are a lot of parameters. I will just go through them one by one. So this P1 being the 0.75 and 0.50, you remember that our coin toss was the ideal probability was obviously 50%, and our probability that we are getting by actually just having 62 heads out of 100 was 0.62 obviously. So if we want to test how many n's, how many times we have to do the entire experiment, then we use this function power.p.test. We put in the two probabilities that we want to differentiate between 0.62, 0.50. What is the significance level, that is the p-value, we want it to be less than 0.05. What is the power? So power of the test is always around 0.8 is a good power level to figure out that you can reject the null hypothesis. So for example, I would tell you here the probability of, say, if I got 62 heads out of a total of 100, the probability was 0.62. So if I put in, so I want to differentiate between a 62% probability and a 50% ideal probability. The significance level is 0.05 and the power is 0.8.
Sir, can you repeat the significance of each once again? I missed that.
See, okay, so what I was trying to tell you is that you want to figure out how many times that you have to toss a coin till you can figure out that yes, if we have a 62% probability, we can actually, like, how you figure use Cohen's h is that you have you what you do is that you look at two different distributions. So one distribution is the ideal distribution where you have a mean like 50% probability of getting a head or a tail. The other is you have a 62% probability of getting a heads rather than a tail. So Cohen's h gives you an idea that how many times you should repeat the experiment till you are able to say yes, the 62% guy is unfair compared to the 50% guy. So how many times should you do it? So obviously we saw that if we do it 5 times, we cannot say that it is fair or unfair. So how, what is the n that should be, that decides like this many times if you do it, you will be able to like positively say that it is either fair or unfair. That is what Cohen's h is about. So the value of h, the if it is around 0.5, you can say that it has a moderate effect size. we are not going to go into that. I'm just want to tell you that this is what we wanted. The number of n's, what number of times you repeat it till you are able to say yes, I can positively say that the coin is unfair. So how many times we should have done it? We should have done it around 134 times. So if, but the moment this value goes even lower, then you have to do it 782 times to actually significantly say that so if, so you have to do it this many times to actually significantly say that the coin is unfair. Is that okay? No. বোঝা গেল না?
ওকে স্যার, বোঝা যাচ্ছে।
না বোঝা গেলে বলা যেতে পারে, আমি আইবার বলে দিতে পারি।
না না, ইটস ওকে, ইটস ফাইন।
Okay. So when your test, you want to figure out the a very, like how big of a difference you want to figure it out, you use this particular function. You put in the probability that is predicted by your null hypothesis and the probability that you predict with your alternate hypothesis, and then this particular function will give you the number of times you have to repeat the experiment to make the test powerful enough to actually say that it is, like if you can reject the null hypothesis or accept the null hypothesis, like this. So that's how you use this function. So there is another term that you guys should know, which is known as p hacking. So what is p hacking? So as you saw that if your value is less, p value is less than 0.05, you can say that your test was significant. So your drug A was better than drug B. So but since we are very much dependent on the value of p and we like to see very low values of p, there is something called p hacking that comes into account. So a good example to figure like what is the difference between this is, in a good research, so on a good lab with very nice people, you actually theorize an effect, say drug A is better than drug B in reducing a particular type of cancer or a particular thing that the cancer is doing, say proliferation. The cancer does not grow big enough, is what you're trying to figure out, that a drug A does better than drug B. So you test, collect a lot of data regarding that and test for only that effect. Is my proliferation hindered by more by drug A rather than drug B? And if your now your p value is less than 0.05, you have good evidence that yes, my drug A is working better than drug B in reducing the proliferation rate of the cancer cells. The other way around that could be done, and which is not very nice, is called via p hacking. You collect a lot of data first, you don't have a hypothesis that you want to test, and you test everything that you want. Say you wanted to prove that somehow my drug A is better than drug B, but you are looking for any way you can do it. So you test for all the parameters and find one particular parameter in which drug A performs better than drug B, and then you conclude that this is how my drug A is better than drug B. Because so instead of going via the original route where you actually make a hypothesis first, you collect all the data, and then finally when you have all the data on your face, you just choose the one that looks good and then say yes, this is why my drug is better than drug B. This is known as p hacking, and it is not very nice and not ethically sound, but people do it all the time. So this is what statistics in a nutshell should look like. You look at your data, you figure out a distribution, you plot the data, you sample some of the data, because obviously you cannot look at every one of the data points in the population, and estimate particular statistics. You make a hypothesis based on this sampling, and then you test that sampling, test that hypothesis, and then look for the p value if it is significant or not. If it is significant, your hypothesis, null hypothesis could be rejected and your alternate hypothesis is actually true, and you accept it and you have found something very interesting to look at. So this is where this is the last thing that I want to go through. So these are so we have been looking at various statistical tools. So most of the time you are testing for difference between two particular things using statistics. So is my drug A better than drug B? Is my coin fair or not? Is the height of people in BSB better than the height of people in CSC? So how do you do that? You actually have to choose particular tests to figure out if, like depending on what kind of data you have, so that you can significantly conclude. So for the coin toss one, we used a binomial test because coin toss is binomial, but most of the data out there would probably fall in a separate kind of distribution which you cannot test very easily. So we have a lot of different tests that we can run to figure it out. So we can, if we start right here, think what type of data do you have? Is it a continuous numerical data or a categorical data? Categorical data means uh, it is not uh, like a continuous set of numbers, but is a discrete set of numbers. So see how many people, like people were preferring Covishield vaccine versus what was the other one, whatever the other one was. So like say people are preferring drug A rather than drug B. So this is a type of categorical data where you have discrete two values that you can choose from. In that case, you either do a chi-square test or a Fisher exact test. If your data is continuous, so a lot of values, say the heights of people in BSc, like biotechnology versus CSC. So you have to ask what is your question. Do you want to figure out the relationship between them or the difference between them? So for the difference between the two heights, I actually want to figure out the difference, not the relation. So I go down this branch, how many groups were there, 2 or more than 2. If it is 2, if it's parametric data, you do a t-test, which is the most famous kind of test everyone does everywhere. If it is more than 2, if it is parametric data, you use something called ANOVA, which is also very famous. If you wanted to figure out the relationship, say height equal to better marks in exams, so you want to figure out a relationship. So figure out what is a dependent variable or a independent variable. You have to either do a correlation or a regression, and then you do a lot of stuff later on. So you actually, this is a very cool graph that you can refer to all the time, and so that you can figure out what kind of test you have to run depending on what kind of question you're asking and what kind of data you have. So we will be dealing with all these like some of these tests in the next class. So there it is. So this is what examples of all of them look like. So students t-test, as we said, you have two categories and a continuous data type. You use student t-test. Chi-square test, you have two categories and you are comparing two different categories depending on that. So both my y and x axis is categorical, then you use a chi-square test. If your x-axis is categorical but your y-axis is continuous, you use ANOVA. So these are the kind of things we will figure out in the next class. So that was all I had for you today. Does anyone have any questions from today's class? Okay. So just I would just like to announce that next week probably we'll be having the class a bit earlier, maybe around 5 o'clock ish, and because I will be traveling for Saturday and Sunday, so it might be that I might not even be able to take a class on next week. I will let you know what the situation is, but positively by next week I will give you the assignment out for the first module so that you can finish it and then we can discuss in the next class. So if no one has any questions, then we can end our class here today. Thank you everyone for joining. See you next week.
Thank you so much.